Oh, nice. That's cool.
Oh no. Another Chris situation. You pulled a Chris. You pulled a Chris.
Look, I got ahead of it. You can't make fun of me now because I already said.
That took a long time.
You pulled the to get a new glass. Get a new pair of glasses.
What's that? This is 8.1 still. We're still in 8.1. All right, let's get started. We have a lot to do today. Our plan is to try and finish up 8.1 today. We might get into 8.2. Don't know. For sure, 8.2 we will start on Thursday. Thursday will be an important day, very important day. All right? So be here. Be rested. All right, so we are going to pick up where we left off. Last class we were talking about sequences. There were a lot of definitions. I showed you some common sequences. The last thing we ended with was factorial, right? I showed you a property of factorials. Now we're going to get right into what's called the limit of a sequence. So remember from Cal 1 that we had limits of functions, right? And we could let in a limit, we could let x go to pretty much anything, but at some point we did let x go to infinity in a limit. And that's what we are going to do here with the sequence. We're going to write down lim n with the arrow going to infinity of a sub n equals L. And what we mean by this is that if you go further and further out into the sequence, if you let n get larger, and that means when you look at the sequence, remember the sequence is just a number followed by another number followed by another number. And if this sequence is infinite, these numbers probably change, right? They don't have to. It could just be like 1, 1, 1, 1, 1, but that would be kind of boring. So if we look at these, the question is, do these get closer to something? Do they actually get closer to a number? And if they do, we will call that capital L, and that's the limit of the sequence. That makes sense to you? The question is just, where is that thing headed? That's it. Now, I'll give you a couple of examples of limits of sequences. And you can see how we're going to utilize kind of a lot of stuff we did in Cal 1. All right, so as an example, let's take the sequence a sub n equals n. And I want you to find the limit as n goes to infinity of a sub n. And let's not make this more complicated than it has to be. This is limit n goes to infinity of the sequence. And the sequence in this problem is defined to be what? N, right? So what happens if I let n go to infinity of n? So what happens is that gets really, really big. This thing gets really, really big, right? This limit actually goes to infinity. We could write out the sequence and see that also. The sequence would be 1 followed by 2 followed by 3 followed by 4 forever and ever, right? So as you go further and further out, that number just blows up, right? It becomes infinitely large. With me? Okay. Now let's change the sequence, make it something a little more interesting. How about 1 over n instead of just n? So for that sequence, we write down the same thing. Let's find the limit as n goes to infinity of a sub n. And then that changes to 1 over n here. And where does that go? That heads towards 0, right? So if we wrote out the terms 1, 1/2 would be next, 1/3 would be next, 1/4 would be next, we can see that the numbers in this sequence are getting smaller and smaller and smaller, approaching 0. And that's something I think most of you can get your head around, right? I mean, you've got something that's getting bigger on the bottom, the top's always staying 1, that fraction should get smaller. All right, with this idea of the limit of a sequence, we have some new definitions. This is what we call the convergence and divergence of a sequence. So these are two different concepts, convergence and divergence. If the limit as n goes to infinity of a sequence equals L, where L is finite. What do we mean by finite? It's a number, right? Where L is a number. Like we did two examples before this, right? The first one, the limit went to infinity. The second one, the limit went to 0, right? Of those two examples, only one of them is finite, and that's the one that was 0, right? The first example I gave you where we got infinity, that would not be finite, all right? So this finite just means a number, a nice real number. So if we take a limit of a sequence and we get a nice number, then we say the sequence A sub n converges. So that's the definition of convergence. A convergent sequence is a sequence that when you take its limit, you get a number. Limit as n goes to infinity. So as you go further out, you get a nice fixed number. We also write A sub n with an arrow, capital L. So this is another way of writing this right here. Because a lot of times we don't want to have to write limit n goes to infinity of A sub n equals L. This says the same exact thing. This says A sub n is approaching L. Got it? Without all the limit stuff in there? Yeah? Just notation? Yeah. All right, thank you. Thank you. All right, so if that's what convergence is, what's divergence? Goes to infinity? Yes, that is correct, but that's not the only thing. There are other cases where we'll have a sequence that maybe flip-flops. Like think about the sequence 1, negative 1, 1, negative 1, 1, negative 1. Is that approaching a number? No, it keeps flipping between 1 and negative 1. Is it approaching infinity? No. So we have to account for that also. So what we say is this. If the sequence doesn't converge, we say it diverges. This is an important concept. It's subtle, but it's important. We are not saying that the sequence must go to infinity or negative infinity to diverge. We are just saying that if it doesn't converge, then it diverges. With me? Okay. All right. So let's take a look now at another example. The sequence, I'm going to define it to be cosine n. I'm going to ask the question, does this converge or diverge? Does this converge or diverge? If it converges, then what's L, right? That's kind of the question you'll be asked on your homework. Most of your homework problems from this section that are really important are these problems. Does the sequence converge or diverge? And then if it does converge, you need to figure out what it actually converges to. All right, so with this one, what do y'all think? Converge, diverge, diverge. All right, so let's take a look. We know that if we're dealing with a sequence, right, we're only allowed to plug in the, what do we call those? The natural numbers, right? 1, 2, 3. We're only allowed to plug those in, right? But we do know what cosine looks like, don't we? Cosine, let's see, pi is about 3.14. 2 pi is about what? 6 point something? 28. So we know that a cosine curve looks something like this. Excuse me if it's not perfect, okay? That's what a cosine curve looks like if we look at cosine as a function of x, where we're allowed to take every value in between here, right? We're only picking out the points at 1. So like up here, we're at 1, and then 2, maybe we're here, and then at 3, we're here, and then 4, we're here, and then 5, we're here, and then 6, maybe we're here. And so if we take out the nice continuous part of this, our sequence is the red dots there. Is that going to one place? No, right? It's not headed anywhere, any one particular. Now, it's always stuck between where and where? -1 and 1, right? But it's not going to a specific number. And that's what we need to have for it to converge. So it diverges, right? By inspection of the plot of A sub n. So I'm explaining to whoever's reading this that my conclusion for divergence is drawn upon just my graphing of the cosine sequence and the dots, all right? And that's good enough for an explanation. See, there's no like math you're doing here. It's more of just analyzing things, right? Okay, how about this? Same question. I don't want to write it over and over. A sub n is -1 to the n over n. And I'm just going to put C/D for does it converge or diverge. And just remembering that if it does converge, we need to figure out what it converges to, right? So what do you think? What is that -1 to the n going to do to our sequence? It's going to keep flipping the signs, right? And so you might be thinking, if we're going to flip signs back and forth between positives and negatives, we're never going to head to something, right? Maybe that's what you're thinking. But the denominator is actually controlling this thing also. The denominator is n. And as n gets large, this ratio is going to want to get small, isn't it? So maybe I could write it a different way. I could write -1 to the n times 1 over n. Just write it like that. And let's actually write out a few of the pieces of the sequence here. So if n is equal to 1, what do we get? -1 over 1. If we plug in 2, what do we get? So -1 squared is 1, and then 1/2, right? So 1/2. What's the next one? -1/3, and then 1/4, and then -1/5, and so on and so forth. If we were to graph this, plot this sequence, it would look something like, let's see, if this is 1 up here and maybe this is -1 down here. When we plugged in 1, we got -1. When we plug in 2, we got +1/2. You know with me? Plugged in 3, we got -1/3, and then 4, +1/4. So we are getting the oscillation back and forth between positives and negatives, but they keep on getting closer and closer to what? 0. But it's kind of almost asymptotic. It's approaching 0. It's never actually going to get there, is it? Okay. But it's approaching it. So going back up here, even though this is going to flip, right? It's going to flip between positive and negative back and forth. This is headed to where? 0. And so it doesn't matter if we have positive or negative. If that number's headed towards 0, the whole thing's going to head towards 0. So my answer is 0. Sorry, I shouldn't put 0 up there. I should put that it's convergent, right? I'm going to write it this way. -1 to the n over n, what, arrow to 0, right? That's me telling you that that sequence converges to 0, right? And that would be it. Now, page 429 in your book has properties. Of the limits of sequences. And I don't want to write them all down on the board. Now, in Cal 1, when you learned about the limits, you were probably told that there's this thing called these limit laws, and they were the properties of limits. And there's a whole set of properties for limits of sequences, and they're very, very similar to the limits that you have with functions. So there's not a whole lot of new stuff here. I just want you to be aware that those limits are listed for you on page 429. All right? Things like if you have two sequences, let me give you an example of one of them. If you have two sequences, A sub n and B sub n, if you're trying to find the limit of two different sequences, what do you think you can do? Find the two limits individually, and in this case, add those results together. So if this one converges and this one converges, right, then you add those two answers together. That's what this converges to. Now, what if you have something like this where one of these diverge? Then it should all diverge? For addition, it does work that way. Okay, so just go review these. All right, they're in the book. I'll kind of reference them as I get to them. I'll let you know when we actually are using something from that page. All right, let's take a look at something called the squeeze theorem. Again, this is another concept from Cal 1. I know in my Cal 1 class we just kind of touch on this. Don't spend a whole lot of time on it, but it comes up quite a bit in different math classes. So let me try and explain it here for sequences. Here's the idea behind the squeeze theorem. I'm going to draw it first. All right, let's say that I have a sequence get some colors here. I'll do it in green. Let's say I have a sequence that does this. Here, you don't have to draw this perfect, all right? Here, maybe it goes here, there, 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 there. Okay, and it's what's happening is it's getting closer and closer to something, okay? You see that? And let's call this sequence right here A sub n. Then I have another sequence, which I'll do in red, which the first one is maybe, here. The second one is maybe here, and then here, and then here, and then here, and then here, 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 here. And it's converging to the same thing. All right? Call that C sub n. Y'all see the picture of what's happening? In the beginning of this, sometimes the A sub n is above the B sub n, and then other times the B sub n is above the A sub n. Agreed? Pardon me? C sub n, thank you. Right? In the beginning, they flip-flop sometimes, right? But eventually, right? Eventually, it looks like that right about at some place in here, right in here, at some capital N, that it's always going to be the green above the red, right? The green above the red. And they're both going to the same place. Let's call this flat line, let's call it L, all right? So if you imagine L, looks like it would be what here for us? It would 0, right? But I could have moved the whole picture up and it would have just been some number. So could I write this down right now? A sub n, arrow L, and B sub n, and C sub n, arrow L. Can I do that? Do you agree from the picture that that's what's happening? Yes?
Yes.
All right, so what the squeeze theorem says is this. If there is a sequence that is between those two sequences all the time, it must also go to L. So imagine that I have to come in here now and draw another sequence, but I always have to stay between these two eventually. All right, so watch me do it. Blue up here, blue down here, blue up here, blue down here, blue here, blue here, blue here, blue there, blue there, blue there, blue there, blue there. So at some point, the blue is always between these two. Then wouldn't you agree that the B sub n, which is the blue one, the B sub n must also go to L? Do you agree? Yes? So I should be able to say this, B sub n must go to L. That's the visual idea behind the squeeze theorem. But let me write it down more formally, because this is not formal enough. Here's the way the squeeze theorem should be written. Have I told you what that means? No? All right, may as well do it now. That's not my own, like I'm making up my own math here. Like that's the mathematical symbol that we use for the word suppose, all right? Suppose there exists a capital N such that A sub n is less than or equal to B sub n is less than or equal to C sub n for little n greater than or equal to capital N. So I know my little n's and capital N's look the same, so I make my little n's small and my capital N's big, all right? So you remember on my picture, I had, what was it? I had, I think, green ones going like this, and I had red ones going like this, and I had blue ones in here like this, right? What this is saying is that suppose that you've got this thing where at some capital N, from that point on, this inequality is always true. The A sub n, which in this case, with this picture would be the red, is below or equal to the blue, which is below or equal to the green, which would be C sub n. I think I got my A's and B's flipped in my pictures, but do you understand it's the same concept? It's like a funnel. We're funneling this thing in between. So suppose that there's a capital N where this is going to hold. Then, if A sub n goes to L and C sub n goes to L, then B sub n goes to L. That's the conclusion. Any questions on this? You get the idea visually? Sure.
So do we just come up with the B sub n?
Yeah, so how is this going to work for us? What we're going to do is we're going to look at a sequence that we're trying to figure out what it does, and we're going to struggle with it. So what we're going to try and do is we're going to try and come up with two sequences, one on each side, that I can definitely figure out where these two go as n goes to infinity. And I'm going to pick these very carefully so that I make sure they go to the same number. Like this one goes to 2 and that one goes to 2. And then that forces the one in the middle to go to 2 also. But the choosing of these two is going to be the challenge for us, as we'll see in the next example. All right, so we'll always be trying to figure out what this one does. We will create these two ourselves. All right, so let's do one. So as an example, a sub n equals sine 2n over 1 over the square root of n. Now there's several ways to do this problem, but I want to use the squeeze theorem to do this, all right? I want to show you how the squeeze theorem works. So converge or diverge, let's see. What does your instinct tell you it does? Converge? What do y'all think? What is the numerator doing of this sequence? It's popping around, you know, it's not going from -1, it's not going back and forth -1, 1, right? It's doing stuff in between too, right? And then the bottom is doing what? Blowing up, getting huge, right? So this is probably going to go where? To 0, kind of like the last one did, where the numbers are getting smaller, they're positive, negative, kind of jumping around. But let's try it with the squeeze theorem. So when I look at that, I need this to be the middle piece of the squeeze theorem. I need that to be the b sub n. But when I write it down initially, I'm not going to write that down. Just watch what I do. I have to work with something I know for sure happens. And I know this much. I think you know this much too. What can I put on the ends of that? What is any sine function bounded between? -1 and 1, right? So does everyone agree with that inequality? That's true? Okay. Now, what I'm going to do is create this sequence in the middle, which means I'm going to have to come in here and divide it by 1 plus root n. But if I do that to the middle term of the inequality, what do you think I'm going to have to do to these? The same exact thing, right? So I'm going to have to divide this by 1 over root n and this by 1 over root n, or 1 plus root n. Now there was something a little subtle here. I thought with inequalities, sometimes we flip them over. When do we flip inequalities over? If you multiply or divide by a negative, the inequality flips. It's like this back in college algebra, maybe even before that. If you're trying to solve that inequality, if I divide both sides by -1 or multiply both sides by -1, it turns into x is what? Less than or equal to -4. Do I need to worry about the flipping here? Did I divide by a negative or a positive number? Positive, guaranteed? Yes, because n is a positive number, right? N is 1, 2, 3. So I know the square root of n is going to be positive, plus 1's positive. So I don't have to worry about the flipping of the inequality, right? Okay, now what I'm hoping we have here is the thing we're trying to squeeze and then have two things on the sides that I know where they go as n goes to infinity. And I hope that they go to the same place. Do they? So take a look at this one right here. What happens as n goes to infinity there? This gets big, that stays at 1, that goes to 0, doesn't it? So this one goes to 0. Over here, don't we get the same exact thing? The top is -1 over something that gets huge, that goes to 0. And by the squeeze theorem, if these two sequences go to 0, then the one in the middle must also follow it to 0. So the answer here would be that this converges to 0 by squeeze theorem. You are always free to use the squeeze theorem on any sequence. You just have to make sure that you can get control over these two sides, which can be challenging sometimes. This one was pretty simple. What about this? Because I didn't mention it when I was working out the problem. In the squeeze theorem, didn't I say that there was a capital N, that like eventually this inequality was true, right? But wasn't that inequality in black here true all the time? Isn't sign always between -1 and 1? So I didn't have like a capital N that it eventually happened. It happened all the time because that's what sign does, right? Okay. No questions on that? Let's do another one. Now, I'm not telling you that you have to use squeeze theorem anymore. I just want to know what this converges, or if this converges or diverges. A sub n equals 0.999 to the n. Converge or diverge? What is your gut telling you here? Diverge? Okay. Any convergers out there? No convergers? Someone break out their calculator for me. If I do 0.999 to the first power, I get 0.999. What's 0.999 squared? 0.9998? What's 0.999 cubed?
It's only 2 9.
Oh, this right here? Okay, thank you. What is it?
997.
Is it? Okay, do 0.999 to the 10th power. What do you get to the 10th power? Just 0.99? What does it look like is happening here? These are getting smaller, aren't they? You want to go for it even bit? How about 0.999 to the 100th? Can you do that? Zero 0.90. Wait.
0.90.
Like that? So, okay, 905. But it's getting smaller, right? It's taking a while, but it is getting smaller. Do you agree? And this comes from the idea that if you take any number between 0 and 1, pick any number in there. So pick an x value that's between 0 and between 1. If you take that x and you raise it to big powers, that's going to go to 0. They get smaller as you raise them to powers. Now, if you take a number that's bigger than 1, the opposite happens, and they get bigger, and that would become infinite. Understand? Okay. So the answer to this is that this converges to 0 by inspection. All right? By inspection. Next one. Two to the n plus 3 over 3 to the n minus 1. Uh-oh. We have trouble here. What are you thinking? What does the numerator do as n gets bigger? That gets bigger, right? And 3 to bigger number, that gets big also. So you have something that looks almost like an infinity over infinity, right? This almost looks kind of like we're getting the form of infinity over infinity. Does anyone remember from Cal 1 what you could do when you have the form infinity over infinity? And we actually did this in here also. L'Hopital's rule, right? L'Hopital? Here's the problem, though. With L'Hopital's rule, you used the derivative, didn't you? Right? And so when we're looking at a sequence, right, we have some sequence here. We know that the top here is a sequence, isn't it, by itself? 2 to the n plus 3, that's a sequence. The bottom is a sequence. L'Hopital's rule would have us take the derivative of the top and bottom separately, right? So imagine that I took just that sequence right there, and I were to graph just that sequence. It would get bigger and bigger. And then I said to take the derivative of it. What's wrong?
You're only taking the derivative of points.
Yeah, how do you take the derivative of points?
Rise and run.
Exactly, but where's the rise and the run? If there's no part connecting these two, remember that the derivative came from the idea of you had a curve, and what we did is we picked some point, picked another point, and then we tried to find the slope of the tangent line between them, didn't we? And then what we did is we moved that point closer, and that adjusted our tangent line a little bit. Then we moved it closer and closer and closer, right? I was saying tangent, that's a secant line, until the points were right on top of each other. When the points were right on top of each other, that's what we define to be the derivative. How can you ever do that at this point? How can I approach if the next point is over there? Like, you see, I can't pick anything in here because it's a sequence, not a function. Understand? So L'Hopital's rule for now is going to fail us trying to do this, right? For now. We will have a workaround. There will be a theorem in a minute. So let's just act like right now we can't use L'Hopital. All right, so if I can't use L'Hopital, and I'm trying to figure out the limit as n goes to infinity of 2 to the n plus 3 over 3 to the n minus 1, do you agree that I could rewrite it like this? And there's no calculus going on here, all right? This is purely college algebra, properties of exponents. Isn't that the same thing? So I'm just using a basic property. If you have x to the n times x to the m, this is x to the n plus m. Same base, different exponents, add the exponents, right? I'm doing that property here, but backwards. I'm starting with n plus 3, and I'm going back to n, 2 to the n, and 2 to the 3. Right? Now, what does that allow me to do? Yes? I have two things now being raised to the n, don't I? 2 to the n and 3 to the n. So again, I can use properties of exponents. Couldn't I do this? 2/3 to the n, right? 2 to the n over 3 to the n is the same as 2 over 3 to the n, because you would do n on both of them. And then what about what's out here? 2 to the third is 8, and then what's 3 to the negative 1? Is that 1/3? And then I could flip it, and it would become a 24, wouldn't it? So we're going to get 2/3 to the n times 24. And where does that head? That does what? Diverge, you'll think? Converge. Converge to 0, why?
Because it's less than 1.
Okay, so this is just like the problem we just did. Remember we had 0.99 to the n, and that went to 0 because we said any number between 0 and 1, if you raise it to bigger powers, it gets smaller. 2/3 is smaller than 1. So if you take that number and you raise it to the n, it's going to get smaller. The 24 out here is never going to change. It's always 24. So you've got a number that's getting really, really small times 24 is still really, really small. So this goes to 0, and it converges. All right? Questions?
Can we know when the diverges?
We will. Don't worry. Okay, how about this one? A sub n equals square root of n cubed plus n over n. What does your gut tell you? Converge, diverge? Where does the top head as n gets bigger? Infinity, bottom? Infinity. So again, we think L'Hopital's rule, but I haven't shown you what we can do with that yet. I've just told you L'Hopital is off the plate right now because this is a sequence, not a function, right? So, Any other ideas then?
Factor in n squared times n plus 1.
Oh,
You want me to pull an n out of the top like this? I could do this? No?
Oh, yeah.
I could do that. I'm just not sure what we're going to gain with it yet.
Never mind.
Okay.
I did it wrong.
Do what? What do you mean? You mean just start taking bigger and bigger values of n and try and figure out what's happening? That would be a way of checking your result, but in no way would that be a way of answering the question on the test. So we have to have a method for this. We have to have a way of determining this. The reason why I say this is because the method is more important than just the calculator punching. Because if I were to say, yeah, you can use your calculator to do these, I would give you ones where your calculator would lead you to the wrong answer. You know what I'm saying? Like, I could very easily come up with an example of a sequence that if you do the first million numbers on your calculator, you're going to think it's going somewhere, but then after a million, it starts doing something else. You see what I'm saying? So it's,
Can
all
you
right.
split it up
Okay,
to limits?
into two limits. You mean limit of the top and bottom separately, or how, like this way? Not sure.
Or the
can you split up the numerator?
Not because of the root, you can't. You can't go into two different ones. We all agree it's infinity over infinity, which is, okay. Ron, you look especially sleepy today. So do you have any idea here? Not feeling good? Okay. All right, so shall I help? There's a couple of different things we could do here, all right? Let's just talk about this for a second. If you did L'Hopital, or like if L'Hopital was allowed, would you want to do it? I wouldn't, because I don't want to take derivative of the top. It's going to be pretty ugly, right? Derivative of the bottom is actually nice. So maybe, I don't know. But there's got to be something else. Let me see. Do you agree with this? Oh, no. It's not going to be that bad. That's the same thing? Okay, now why did I do that? Can I do that? Now I can split it up. See, what I did is I forced them both to be under a root. So I had to square the n and put it under a square root to create the n. And then I made one fraction out of it. And now, splitting it up into 2, you get n cubed over n squared, which is n. And then over here you get n over n squared, which is 1 over n. Now let n go to infinity. What happens? 1 over infinity goes to 0. Infinity, square root of infinity is infinity, right? This heads to infinity. So what do I say? It diverges. We knew that it was infinity over infinity. That's never enough to be able to determine the answer. So we had to do something algebraic to make it happen. Shall we do another? Of course, yes, yes. So how about this? Sine 4n over tangent 3n. Hold on a second. I don't want this. Hold on. No. No. Okay. Natural log n over n squared. That one's a little more along the line.
Professor,
Yes.
whenever it converges, do we just write converges or we write the number as well? Like
If you write like that's the sequence and then you put an arrow and you put your number here and you box that up, I will understand that you mean it converges. But if you write this infinity, please just write diverges so that you show me you understand that this means divergence.
So when it converges, the number has to be there. You can't just write converges.
You need to, yes. So the question is, does it converge or diverge? If it converges, what does it converge to? All right, so how about this one? Infinity over infinity, right? That gets big. Natural log gets big as n gets big. N squared gets big. You have infinity over infinity again. Now, if we could do L'Hopital's rule, would you like to do L'Hopital on this one? Because derivative of the top is nice, isn't it? 1 over n, derivative bottom is 2n. That would probably work out pretty nice. But again, we can't just use L'Hopital's rule just for the heck of it. So what we have to do is have a theorem first. There's a theorem that says the following. Suppose f of x is a real valued function. What do I mean by that? I'm looking at a function where x takes on real numbers. So now I've got a nice like a nice traditional graph of a function instead of all the dots. So suppose f of x is a real valued function. Then if the limit as x goes to infinity of f of x equals L, then the limit as n goes to infinity of f of n equals L, where n is a natural number. Can anybody explain to me what the hell this theorem is saying, like visually? Does anyone understand what any of that means? F is a function, right, where x can be any number. I look at that function, I look at what happens as x goes to infinity, and it turns out to be some number L. The conclusion is what? That function, that same function, restricted to just the natural numbers must do the same thing. So graphically, here's what we're saying. If we have a function f that's defined wherever, and it's flattening out to some L value out here. It's getting closer and closer to this L, right? So if that's happening, then if you restrict the f to just the dots, just the natural numbers, then it's going to have to go to the same place, right? Yes? So how can I tackle this problem here using this theorem? Look at this as a function of x first. Replace the n's with x's and look at it as a real valued function. Figure out what it does. Whatever it does, that does. Understand? So we are going to be able to use L'Hopital's rule. But the subtle thing is that we're not using L'Hopital's rule on a sequence. We're actually converting the sequence to a function of x, figuring out what happens to that, and then using the theorem to go back and say what the sequence did. It would be incorrect for you to use L'Hopital's rule on a sequence. All right? So here's how I'm going to do this. First, I'm going to look at this. Let's look at the limit as x goes to infinity of natural log x over x squared. So when I write down x, is that okay that we have an understanding between us that when I write x down, x is now a real number, right? I don't want to have to write that every single time I write this. The assumption here is that x is a real number. I don't expect you to write that x is a real number every single time either, but you better switch it from n to x. If you don't do that, then you will get deducted points. Sorry, I mean, it's an understanding of what's happening here. So we're going to look at this. Now, can I use L'Hopital's rule on this? Yes. So I come in here with L'Hopital's rule. Because I have infinity over infinity, take the derivative of the top, take the derivative of the bottom. I believe that's just 1 over 2x squared. And where does that go? That goes to 0. I'm not going to box that and say that's my answer. I'm going to now draw the conclusion, right? I need to state the conclusion. How do I say this? Therefore, right, this sequence converges to 0. So we actually have a symbol for therefore. Like this was, suppose I already erased it. What's the symbol for therefore? Three dots like that. Okay, that means therefore, all right?
Like the predator?
I'm going to, kind of like the predator. It's not exactly the predator. Pretty close. Pretty close. Therefore, right? Therefore, the limit as n goes to infinity of natural log n over n squared equals 0. You could have written instead of this, you could have written natural log n over n squared goes to 0.
Yes, put in the conditional that x is a member of all real numbers.
Pardon me?
Do you have to put that x as an element of all real numbers?
Ron, I'm going to cut you slack because you're not feeling well, but I already answered that question. Do you have to write this?
No.
No. Okay.
In the answer.
No. No. You mean over here?
Yeah.
Uh-uh. As long as you switch from n to x, I understand that you understand that x is now, that this is now a function of x and you're drawing the whole curve nice and smooth. The theorem allows us to draw the conclusion that the sequence does the same thing. All right, we good? All right. Another example. All right, you remember that exclamation point from last class, right? I will write down on the side as a reminder of what it is. N factorial was n times n minus 1 times n minus 2, all the way until I get down to 1. As an example, 5 factorial is 5 times 4 times 3 times 2 times 1, right? And we talked about properties of factorials last time, right? And I want to point out something that even if I stressed it last class, I want to stress it again, all right? We have this very special property that's going to be used throughout the next week or 2 or 3, till the end of the semester maybe. It's this property. N plus 1 factorial equals n, n plus 1 times n factorial. Big time property right here. Now let me just explain what this is, all right? Let's say I write 5 factorial. According to this property, the n plus 1 we have here is 5, right? Yes? So this should be equal to 5 times what? If n plus 1 is 5, then what's n? 4. What, factorial? Do you all agree with this? What is 4 factorial? 4 times 3 times 2 times 1. So this piece right here, 4 factorial, is that. But if you put them all together, 5 times 4 times 3 times 2 times 1, it's 5 factorial. What is n factorial? N times n minus 1 times n minus 2 times n. So do you agree if the rest of this is n, n minus 1, n minus 2, n minus 3, if I put those all together with that in front, it's that? Yes? You have to see this. I mean, I can't force your brain to understand that. You either you're going to see it or you don't. Okay, so with this in mind, let's see if we can handle this. First of all, what's the top headed to? What's 5 times a big number factorial? Big number, right? So it's coming to infinity. This one on the bottom, same thing, right? So then you say, all right, well, wait a minute, infinity over infinity, we just used L'Hopital's rule, didn't we? So why not just do that again? Just switch this to function of x, take the derivative, and then, top and bottom, and then go ahead and figure out what happens. Why can't we do that? What the hell is the derivative of a factorial? You can't do it, okay? Remember, I said factorial is only defined when these numbers are integers. You can only do 0 factorial, 1 factorial, 2 factorial. So you know how I was saying earlier that what we do to be able to get around it and use L'Hopital is that we treat it like a function, then we come in here with the dots. The problem is you can't treat a factorial like a function of real numbers. You're not allowed to. So you can never get it over to L'Hopital's rule. So you got to have some other way of dealing with it. And I'm giving you the hint that that's going to help us. I'm not sure this really sunk in or not. I don't think it did. I just get the sense it didn't. Okay, could I write it? I'm still going back to that in a second. Could I write 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1? Yes, I could do that to write 9 factorial. But 8 all the way down to 1 is really what? 8 factorial. So this is really 9 times 8 factorial.
And your n is going to be 8.
N would be 8 here in that formula. But more importantly, here's what I want you to see. If you start with the factorial, what you can do is write down the thing that's here, right? It's a 9 here. You can write that down. And then next to it is a factorial. And the thing that goes here is 1 less than what was here, right? So if I wrote 123 factorial, I could write that as 123 times what? 122 factorial. Please keep in mind that the factorial is attached to the 122. A factorial is not like a number that you could commute and flip back and forth and slide wherever you want. That factorial is attached to that number. Yes?
But sir,
Yes.
by that, I guess, logic, could you do 121 factorial, 123, 122, 121 factorial?
Absolutely.
That's, okay.
And you could keep going, right?
I think someone created that so that they could save time when they're writing all this crap out.
Yeah, it is just notation. That's all it is, right? You could keep doing this. Go, next one is 120 factorial and remove the factorial here. Yes?
If you do this formula, like the second one, then it's going to be n plus 2, right?
Yes.
Instead of n plus 1?
That's right. So think about it the other way around, though. Think about it as you started with 123. If you write it this way, you actually put the 123, you peel off 1, right? You peel off, you take it down by 1, and then you go and you take it down again by 1, and then it's that factorial. Now, do you see how I'm going to use that here? These are almost the same, right? 5n and 5n plus 2. This one is only 2 more than that one. So if I peel this twice, I should get the 5n factorial to appear, shouldn't I? And then they should be able to cancel. That's the idea. Now let me see if I can write it down and you agree. 5n factorial over, now I'm going to rewrite this one. This is 5n plus 2. And then the next one should be this take away 1, right? Which would be 5n plus 1. Isn't that what happens when you take 1 away from that? And then factorial. But I'm going to go even one more. Well, maybe I'll do that. Okay, do that. Does you all agree with that? Yes? Now I'm going to take the 5n plus 1, and I'm going to peel 1 off of that, and we would get this. Five n plus 2, 5n plus 1, and then what? 5n factorial. And now those factorials are identical, and they cancel. And now you just look at that expression right there, okay?
So you just brought it to like 0 factorial?
Brought it to,
Because there's no more 1.
there's no more factorials. All that's left is this. 1 on top, 5n plus 2, 5n plus 1. That's all that's left. Now take the limit as n goes to infinity. What is the limit as n goes to infinity of this? Is 0. So it converges to 0. Let's just do a show of hands, okay? Just an honest show of hands here, because this right here is very fundamental as we move ahead. Does that, who is okay with what I did here in the peeling off? Yeah? Okay? Okay.
Can it only be done with factors like integers? Like it can't be done via multiplication? You can't touch that?
What multiplication?
The 5n
You can't touch that.
with factorial? Can't do anything else?
That is correct. You cannot. What happens in that property with the factorial is that you're subtracting 1 each time. And because this is multiplication, you can't do anything to that. So watch. Maybe this will help address 5n factorial. Damn it. 5n in parentheses factorial is equal to 5n times what? Take it off. 5n minus 1 times, take it down. 5n minus 2 times 5n minus 3 until it gets down to 1. That's what that is. So the 5n never got touched, does it? Compare that to this. What's the difference?
It's part of the primary.
What's the factorial on here? Just the n. Here, it's the whole thing. So the difference between these two expressions is that this is 5 times n minus 1 times n minus 2 all the way down to 1. See the difference between that? Critically important that you understand those parentheses mean a big, big thing there, right? We could spend an entire week or two on just factorial fun, but we don't have time for factorial fun in here. We're going to get more experience with factorials as we move on. We'll have no choice. All right. Theorem. A nice test for convergence but you must be careful with this. Okay, I'm about to give you a theorem that's going to be a way for us to test whether or not something converges or diverges, but you have to be extremely careful when you use this. All right, here it is. The theorem says if the absolute value of a sub n goes to 0, then a sub n goes to 0. Let's read through the theorem. The assumption here is that you have a sequence and that when you take its absolute value and take a look at that, that heads to 0. The theorem says if that's true, then the sequence without taking the absolute value also goes to 0. All right? Let's see this in use. As an example, let's look at the sequence that we looked at earlier. -1 to the n over n. We did that earlier. And we did it, we kind of graphed it a little bit, and we kind of just worked through it mentally. But let's see how this theorem would work. First of all, what is the absolute value of a sub n? What is that? Well, -1 to the n over n, absolute value, right? So let's say I plugged in some numbers here. Like I plugged in 1, I would get a -1 there, right? And I take the absolute value of -1, and that would be what? 1? So no matter what happens up top, do you agree that once I hit it with an absolute value, it's going to be 1? And then what about n? If I take the absolute value of n, I'm going to write it this way. All right. Absolute value of -1 to any power, that's going to be 1. I think you just agreed. What about the absolute value of n? It's just going to be n. Why? It's a positive number anyway, right? N was 1, 2, 3, so it's just n itself. So the absolute value of the sequence we're looking at, the absolute value of it is 1 over n. And according to this theorem, if we take the limit as n goes to infinity of the absolute value of a sub n, right, if that goes to 0, then what can I say about the original sequence? It also goes to 0. So let's just check it. This is limit n goes to infinity. What was the absolute value of a sub n? 1 over n. And that goes to 0, right? Therefore, -1 to the n over n goes to 0. So we're starting to get, I hope you're starting to see that the flavor of this whole section is that when you're given a sequence and you're asked, does it converge or diverge, there is not one thing you pull out to attack every problem, right? Sometimes you'll need L'Hopital's rule, you'll have to convert it over. Sometimes you can just do it without anything. Sometimes you have to look at the graph and get an idea what's happening. I mean, we could use this theorem, and this is just going to continue to happen as we progress through this chapter. It's going to be more about, can you draw a conclusion? Can you actually start with something and then write down the information to convince me that you did what you're supposed to do, right? Is your conclusion correct? A lot of times on these tests that cover Chapter 8, students will get to the correct result but not show the correct work for the result. So they'll draw a conclusion, but their logic behind it is not right. See how everything is written here? Here's a sub n. Okay, what's the absolute value of a sub n? Oh, it's this. Okay, what's the limit of the absolute value of a sub n? It's this. Oh, that goes to 0. What does that mean? Well, that means that this goes to 0 by this theorem, right? All right, so sometimes not. See, that's the thing. You got to know when to pull out what thing to attack the problem.
So I mean, if you decide I'm going to use that theorem, do I have to write it down? Would you have to write it down?
No, I wouldn't require you to. All right, how about this one? What does this sequence do?
Change the negative positive.
Flip-flops back and forth between 1 and -1, or starts at -1, then 1, then negative. So does it converge or diverge? Diverges, right? Diverges. Watch somebody fumble this thing up big time. Ready? Here it comes. Here's me on a test. Okay? Having tried, I don't remember what that does. I'm going to take the absolute value of a sub n, which is the absolute value of -1 to the n, which is just what? 1. Not even to the n. Well, you could, but it doesn't matter because 1 to any power, -1 to any power is going to be 1 or -1. We take the absolute value of it, it's 1, right? So what I can say from this is that the limit as n goes to infinity of the absolute value of a sub n equals the limit as n goes to infinity of, well, what was this? 1. And that n doesn't even have an issue, right? So the answer here is what? 1. Therefore, what? -1 to the n converges to 1? Wrong. Why? We know it diverges, but why? What's wrong with this?
If it's oscillating, then you can't really tell like, how close it's getting. I think that's
Yeah, yes, you're overthinking it though. Hold on. What does the theorem say? It says if the absolute value, right, if that limit goes to what? 0, then the original one goes to 0. That didn't go to 0. And since it didn't go to 0, you throw the theorem out the window. You can't use it. The theorem only works if this limit right here goes to 0. So you see how you could incorrectly use a theorem and draw a conclusion that we all know when we started the problem wasn't correct? So you have to be careful how you use these things. Pay attention to the little subtleties in there. So the theorem fails here. This right here must go to 0 for the theorem to apply. So that is incorrect. That's what I mean by drawing a conclusion, thinking you've got the right thing, and it's wrong. Ready for another one? Yes, yes you are. You're excited. Limit n goes to infinity, 1 plus 2 over n to the n. We're going to be a little behind, okay? I have fallen behind. It's okay. Always happens. 8.1 always takes me 2 days. I don't know why I ever think I can get through it in 1 day. I could go through 8.1 in 1 day, but there's so much in here that if we leave something out, it's
This is 8.1?
it's still 8.1. We're still in sequences. When we come back, we start series. All right, you ready? What happens as n goes to infinity? 2 goes, shoot, I should have written the original sequence. Sorry, I should have written this and asked you, does it converge or diverge? That's what I should have done. Does that converge or diverge? And then you would have come in here and said, okay, I need to figure this out, right? So 2 over infinity, that's going to go to 0, right? And then plus 1 is going to be what? Just 1, right? Raised to the what? Big number, right? Now, you have to be extremely careful. Because are we saying that this base is 1? It's getting close to 1, right? Is it ever actually getting there, though? Think about it. If I plug a huge number in here for n, 2 divided by that huge number, isn't that a tiny little number? It's getting closer to 0, but it's tiny, isn't it? So I have 1 plus a tiny number. That's not 1, is it? So if I take a number that's really close to 1, so I'm just going to say here, this right here is a little greater than 1, isn't it? This number right here is a little greater than 1. And I raise it to this huge power, what happens? It kind of depends on how big the power is and how close that is to 1, doesn't it? And in Cal 1, we called any time we got something like this an indeterminate form. This is the same as having infinity over infinity, or 0 over 0, or infinity minus infinity. These are all indeterminate forms from Cal 1, this included. So there is a section in Cal 1, I think it's chapter 4, section 7. I already asked you to review that when we went back and did improper integrals. I again stressed that you go back and review that if you didn't. I can't spend more time going over stuff from Cal 1 in here. This is indeterminate, and you need to recognize that. So when you have this indeterminate form, does anyone remember what we do to determine what it is? No? Okay, it's all right. I'm going to first switch this over. So what am I doing here? I'm looking at my sequence as a function of x, right? I'm moving this thing from n's to x's so that I can use L'Hopital's rule. L'Hopital's rule, though, is only allowed to be used on these two forms, right? You're not allowed to use L'Hopital's rule on that. We have to turn this into this before we can use L'Hopital. So let's see if this rings a bell. You take this, and we call it something like y. Anyone remember yet? Take the natural log on both sides. That's correct. We're going to take ln on both sides. So I'm going to have natural log of y over here, limit x goes to infinity, natural log of the right side. Why do you do natural log? What does it allow you to do next? Bring this power x out in front of the log. That was a property of logs. So now we're looking at this. Natural log y equals limit x goes to infinity of x times natural log of 1 plus 2 over x. And now we'll do a quick check to see what happens. As x goes to infinity, this goes to infinity, doesn't it? 2 over infinity goes to 0. 1 plus 0 goes to 1. Natural log of 1 goes to... So this is going to infinity, agreed, times natural log of 1 is... That's natural log of 0. Natural log of 1 is 0. So what's happening here is that this is getting huge, this is getting really small, getting close to 0. That is still an indeterminate form from Cal 1. But anytime we have this form in Cal 1, what we do is we pick one of these and we drop it to the bottom. So I'm going to take the x that's out front, and I'm going to drop it to the bottom. When I do that, it has to be a 1 over x on the bottom. And then you play the same game. What happens as x goes to infinity? We already know that this is going to turn into a 1. We already know the natural log of 1 is going to be 0. Then 1 over infinity, that gets close to 0. Now we finally have 0 over 0. So there's a lot going on here, right? Now we can use L'Hopital. So with L'Hopital, I'm just going to work with this piece right here. The left side is still natural log y. limit x goes to infinity. And what is the derivative of this up here? Well, I'll do it for you. 1 over 1 plus 2 over x times negative 2 over x squared. So you have to do chain rule. Derivative of natural log of something is 1 over it. Derivative of the inside of that is negative 2 over x squared. I'll let you do that yourself because that's Cal 1 stuff. Okay, derivative of the bottom, negative 1 over x squared. You see anything? The x squareds. You basically can multiply the top and bottom here by x squared, and it'll cancel here, and it'll cancel here. What about the negative 2 and the negative 1 there? Negatives and negatives gone. It's a positive, right? So you have natural log y equals limit x goes to infinity of 2, which is this 2 being moved up here, over 1 plus 2 over x. And then now let x go to infinity, and what do you get? Two. You get 2 on the right side. So what we have is this, natural log of y equals 2. But remember, didn't I come in there and I took this limit, right, that we were looking at, you go back and look at it if you wrote it down, and I called the limit that we were trying to find, didn't I call it y? Yes? And then I took natural log on both sides. I need to get this back to y. So I'm going to take e on both sides to get it back to y. So at this point, I take e of the left side, e of the right side, and the left side becomes y, and then e squared is the right side. So it converges, doesn't it? Converges to e squared. So now what I would say is therefore 1 plus 2 over n to the n converges to e squared. I would say 93% of that problem was Cal 1. The other part was just knowing that you had to switch from a sequence to a function, and then at the end the function back to the sequence. Other than that, there's nothing new in terms of any new calculus there. What do y'all think? Are y'all okay? Tedious? I just want to do one thing. Just summarize something we talked about earlier. Yes. This is just that problem that we kind of started earlier with, like 0.999 to the n. What did we say this went to? 0, right? The reason why is because we were taking some number, r, and we were raising it to an n power. And that number was what we said between 0 and 1. And so we said that that would squash down to nothing eventually. So this summarizes that. It says that if the r is less than or equal to 1, greater than or equal to negative 1, this thing is going to go down to 0. What if it is 1? What if r is 1? What's 1 raised to any power? 1. So it would just be 1, 1, 1, 1, 1. Does that converge? 1, 1, 1, 1, 1. What does it converge to? 1, right? So in the case that r is less than 1 or equal to 1, it's going to converge. Any other case, if r is outside of this, so if r is negative 1 or negative 2 or 5 or pi, or doesn't matter, it will diverge. Okay, we have one last concept here. We got 15 minutes. I don't know how this happens. Some definitions. A sub n is said to be increasing if a sub n is less than a sub n plus 1 for all n. An increasing sequence should go up, right? As you move from left to right, it should go up. So the nth term of the sequence, or the nth number, should always be smaller than the next one, shouldn't it? So this one would be here, the next one would be above it, and then the next one after that would be above that one, and so on and so forth. So that's what it would mean to be an increasing sequence. A sub n is said to be decreasing. What am I going to have to do? If a sub n is greater than a sub n plus 1 for all n. So that just, it's the opposite. You have a dot here, the next one has to, this one has to be bigger than the next one. And that one has to be bigger than the next one, next one, next one. So that would be decreasing. Yeah? In either case, a sub n is said to be monotonic. Monotonic. So a monotonic sequence is either increasing or decreasing, right? So either one. If it's an increasing sequence, we call it a monotonic sequence. If it's decreasing, we call it monotonic. So monotonic doesn't quite tell you which one it is, right? It just tells you it's one or the other. All right, more definitions. So I'm going to continue. A sub n is said to be bounded above. What do you think about when you hear that? Bounded above. If now this symbol right here means there exists. It's a capital E backwards, means there exists. A capital M, such that a sub n is less than or equal to, strictly less than, capital M for all n. Look at this definition as being like a roof, a ceiling on the sequence. It's an upper bound. So we draw a sequence. It's doing whatever. It's moving around, a bunch of dots in there, right? If it's bounded above, then there's a capital M that is working like this roof. this cap that our sequence can never go past. And so you can have a sequence doing all kinds of stuff in here, but that it is bounded above. Make sense? Pretty intuitive? The wording of it's kind of weird, I mean, the way this is written. There exists some number, m, so that the sequence a sub n is always below that m for every n you could ever pick. A sub 1, a sub 2, a sub 3, any n, it's always going to be below that. Guess what the next definition is? Bounded below. And what we're going to do for below is we're going to use a little m, and we're going to flip that inequality over. That's all that's going to happen. So bounded below, there exists a little m such that a sub n is bigger than little m for all n. So that would look like this. Little m. This is the picture for bounded below. Your sequence could be doing all sorts of stuff. It's just got to always stay above that line. Then it's got a lower bound to it. Questions?
So could the sequence ever equal the little m? Or could it land on the line?
Well, then we wouldn't say that that's the capital. Like, let's say this is little m, right? If your sequence lied there, like would land on that, then our little m would be any number that would be below that. Okay, so if that actually goes and that's the lowest point, we should be able to find something lower, right? That would be our lower bound. All right. If a sub n is bounded above and below at the same time, because you don't have to be bounded. A sequence, first of all, never has to be bounded. It could just be bounded above. It could be just bounded below. But if it's bounded above and below, so if a sequence is bounded above and below, we say a sub n is a bounded sequence. I've never liked this definition, but it's the way it is. So I guess this is where it comes from, the part of it I don't like. If you say that something is bounded, at least for me, it would make more sense to mean that it's bounded above or possibly below. And then in that case, it's bounded at least in one direction. But when we say bounded here, we mean bounded above and below at the same time. That's the only way you can ever say a sequence is bounded, if it has an upper and lower bound. Right? It's fixed between two lines. And that leaves us to the monotonic bounded sequence theorem. This is the last theorem of the section. Every bounded monotonic sequence what? Must converge. Very good. Let's see if it makes sense why. That's right. So you've got a sequence in here that's bounded. Bounded means it's got a roof and it's got a floor, right? It always has to stay between those two, right? That's what it means to be bounded. That's what this is. Monotonic means what? It's either going up and always going up or down and always going down. So let's just say it's up and always going up. Then I don't care where you start me, okay? Start me, you tell me where. There, okay, right there. Now, if my next one, that's plugging in one, if my next one has to be above that, right? Then the next one above that, and above that, and above that, but there's a roof as to how high it can go, then I have to start flattening out, don't I? And what I'll do is I will asymptotically approach some bound up here, won't I? Because I can never come back down. So there's got to be something. Now, it doesn't have to be the capital M. It can be below it. But it's got to go to something. Okay? It's got to. I remember talking with someone one time about this state. Oh my God, 4 minutes? You got to be kidding me. Well, I don't really have time to give you an example, but let's talk. I'll tell you what I was going to tell you in a second. But what does this theorem allow us to do? If someone asks us, does a sequence converge or diverge? This theorem says that if we check for two things, we can tell you if it converges, right? We have to first show it's bounded. If I can show you the sequence is bounded, that's the first condition. The second condition is to show you it's monotonic. If I can show you those two things are true, I'm guaranteed to converge. What this theorem doesn't allow you to do is tell someone what it converges to. It just allows you to conclude convergence. And a lot of times, as we're going to see as we move into chapter 8, through chapter 8, just being able to say convergence or divergence is good enough for what we're doing. That's all we need. Okay, where's my book? Let me give you a homework assignment. What I was going to tell you, the little story I was going to tell you is when I was kind of a younger mathematician, and I was still quite a bit naive and not knowing, thinking I knew a lot more than what I knew. This is going to sound so bad. I'm just going to turn this damn thing off.